Hi, it's Mr. Blystone. So here is video 1 for Unit 1 of Calculus, and we're talking about the concept of instantaneous rate. So let's kind of look at a motivating example here. So if we have a door, like in the figure here, if we push it open and it has one of those automatic closers, it opens fast at first, slows down, stops, starts closing, then slams shut. So as it moves, the number of degrees from its closed position depends on how many seconds it's been since you pushed it. So the question we can answer at any particular instant in time is the door opening or closing, and how fast is it moving? Okay, so let's take another look. So here is an equation that models the number of degrees it is from its closed position in 7 seconds. So we push it open at t equals 7, and it slams shut, or at t0, and it slams shut at 7 seconds. So while it's in motion, the number of degrees it is from its closed position is modeled by this equation. So we have 200t times 2 to the t minus 1, negative t. And we want to know how fast it's moving with the moment when t is 1 second. Now, how fast? Well, let's just look at the graph first. So at t is 1 second, let me make a little dotted line so we can kind of see something here. So at 1 second, our graph is right about there. Let me change to a little dot so we can see it. Let's go a little thinner. Excuse me. I have to tell it which one. All right, so if we look right there, well, the position is going up. It's not at its farthest point from being closed, so it's still opening right here. And here's where it would start closing. So it's still opening. And it kind of looks kind of steep, but it's starting to level off. So it's going to be kind of moving a little bit fast, but that's about all we can tell. We don't really have numbers. Now, we have an equation. So we want to know how fast. We want to know a rate. So what can we do? Well, we can find time, we can find degrees. We can at least do that. And we could say, okay, so at 1 second. So our equation, let's rewrite that so we know, is d equals 200t times 2 to the negative t. All right, so we could solve this for d of 1 at 1. So we could say d equals 200 times 2 to the negative 1. And we could say, if we use our calculator to find out the value of that, its degrees at that time is 100. So we know it's 100 degrees from its closed position. Well, let's see here. What about 0.1 second later? What is it there? Well, that would be 200 times 1.1 times 2 to the negative 1.1. If we find that one out, if we look at that, well, let's see here. 200 times 1.1 times 2 to the negative 1. oops, to the negative 1.1. Well, that is 102.6336291. So let's see, 634. That's fine, 634. Okay, so we know that in 0.1 seconds, 0.1 seconds, it moved, D moved 2.634 degrees. So in 1 second, so we could say in degrees per second, so it was moving at 26.34 degrees per second. But that's only an average speed. That's only an average speed. So what can we do? Well, let's see. We want an instantaneous speed at a point where that time interval is 0 seconds. Well, let's think about how would something actually move in 0 seconds? Well, in 0 seconds, it wouldn't move any. So let's think about that. 0 seconds, no movement. So it would go 0 degrees in 0 seconds. Does anyone see where this is a problem? 0 over 0. 0 over 0, we'll later learn it's called indeterminate form, if you haven't heard that already. We can't tell anything. We can't divide 0 by 0, but it's not like a number divided by 0. It's worse than that. 0 over 0, it doesn't tell us anything. We have 0, but we want 0 groups of 0 things. It breaks your mind. So this doesn't tell us anything. So this means we need to figure out more information. Okay, so I tell you what. Let's, instead of do that, let's see if we can find a smaller time interval. Let's make our time interval smaller. So let's go from 1 to 1.01 second. And then let's see about 1 to 1.001 second. Let's just do those. So we have D equals, so we know 1, so let's just put that here. So for 1, D equals 100. So D for 1.1, we have 1.01, 200 times 1.01 times 2 to the negative 1.01. So let's see. Okay, well, in that many seconds, in 0.01 seconds, the change. So let's use something for change. So in math, we often use the symbol of delta, a triangle. So the delta distance, the change in distance, is 0.302 degrees. So approximately, so 3.302 degrees in 0.01 seconds. Or we could say 30.2 degrees per second. Okay, what about 0.001 second? Well, let's see here. D equals 200 times 1.001 times 2 to the negative 1.001. If I do that, oops, not quite. We get, it changes by, so the delta D is 0.03064. So I hope you're noticing, and that's in 0.001 seconds. So if we take away, that's 30 point, so about 30.64 degrees per second. So I hope you're noticing that as we make the interval smaller, the amount of change in its position is really kind of, it's getting smaller. It's not changing as much. So let's look at some of those values in a table here. So if we go from 1 to 1.01, we see 30.23420, 64000. If we add another 0, it's 0.684. And we keep adding 0.685. So it seems like as we get really, really, really close to that no time at all, it's approaching some number that's getting very close to this. A limiting number. So using the same idea, why don't you try on your own to find the instantaneous rate at t equals 3 using this equation? Do the same idea we did. Look for the change in a small interval and see if we can find something close to a limiting value ourselves. So pause the video, see what you can do. I suggest using a calculator. I suggest plugging the equation into the graphing calculator in y equals, and then using the table feature and changing. Go to second and push window. That's the table setup. And go down to where it says independent and change it over to ask. So then you can put in your own values and you can see it come out. All right, so try it yourself and we'll see what we get. Okay, so what I did was use a spreadsheet to make a little table here like you probably could have done. And I bet D, and change in D, and notice. So as we add more zeros, as we get really, really close to 3, the change is about negative 26.986. It's kind of honing in on that, around there. Now, how is it changing negative? What does that mean? Well, let's look at our graph again. Let's go back to our original graph. Here's one right here. We can look there, but let's go to this one. So we're looking at t equals 3. So we have t equals 1 up there. Let's do 3. So 1, 2, 3. So this is 3. And again, we go up to the graph. Try to be straight as we can. Let me highlight the line. Let's thin it out. And let's change it to a dot on this end so we can see the dot. So what we can see here is that it is closing. It's moving closer to its closed position. So here it's moving farther away. It's increasing. Here it's decreasing. So it should be, the change should be negative. And it is. Again, our limiting value is about negative 26.986. Okay. So the instantaneous rate of change of the dependent variable is said to be the limit of the average rate of the average rate as the time interval gets closer to zero. This limiting value, we call it the derivative of the dependent variable with respect to the independent variable. So basically that limiting value of its rate of change as we get closer and closer to instantaneous, we call it the derivative. All right, so the problems you should try are 1 and 2, and on 2, just do parts A through D. All right, thank you very much. Hope this video helped, and keep on learning.